All right. So in this lecture, we'll learn about the symmetric group. As a starting point, given a set, call it S, we define AS as the set of all bijections mapping S onto S. So for instance, let's S be the sets containing 1, 2, elements 1, 2, and 3. Then AS is the set consisting of the following 6 elements. First, let's call this map F1. F1 will act on the set by sending every element to itself. 1, 2. 1 goes to 1, 2 goes to 2, 3 goes to 3, and so on. F2 F3, 1 goes to 2, 2 goes to 3, and 3 goes to 1. F4 act as follows: 1 goes to 1, 2 goes to 3, and 3 goes to 2. F5 1 goes to 3, 2 goes to 2, and 3 goes to 1. F6 1 goes to 2, 2 goes to 1, and 3 goes to 3. So you can see that we have 6 elements, and if you try to find any other bijection which is mapping the set S onto itself, you'll see that it has to be one of these elements. Now, if we let S be the set of all elements containing 1, 2, 3, 4, then the set of all bijections of S onto S is in a one-to-one correspondence with the sets of all possible permutations of S. So in other words, the set A of all bijection of these sets has really 4 factorial elements. So that would be 24 elements. Notice that in the previous example, this set here has 6 elements, and 6 is actually 3 factorial. Okay, so we're going somewhere with these observations here. In generalizing this concept, let us suppose that S has n many elements. Then the symmetric group degree n is defined as often denoted Sn, or A of S here will be the set of all functions taking S onto S such that F is a bijection of S onto S. For instance, we saw earlier that S3 has 6 elements, and S4 has 24 elements. So this leads us to the following proposition: has n factorial elements for any natural number n. We'll prove this result by induction. The base case is clear because there's only one bijection sending a singleton to itself. Now for the inductive step, let us assume that Sk has k factorial many elements for some natural number k greater or equal to 1. And let S be the set containing all elements from 1 to k plus 1. And let's define Ij as being a set containing all bijections such that f of j goes to 1. Then the sets I1, I2, all the way till ik plus 1 is going to give you a partition of the symmetric group of degree k plus 1. Now, I want you to pause the video here and try to completely understand these ideas for yourself. Once you do that, then you will be able to proceed with the rest of the proof. By the inductive hypothesis, Ij has k factorial elements in it. Now, right? Why? Because each Ij is fixing one element in the set S. So all the permutations inside that set are essentially just acting on k elements. But we have already assumed that the set of all permutations of degree k is equal to k factorial. So every Ij set will have k factorial element. Now, Sk plus 1 has how many elements? Factorial plus k factorial plus k factorial all the way till k factorial element. Why? Because each one of these represent the number of elements. So this is the number of elements in I1, this is the number of elements in I2, the number of elements in I3, all the way till k plus 1. So here we have k plus 1 many addends. So this will amount to k plus 1 times k factorial. Now, if you work this out, this is precisely k plus 1, and k factorial is k, right, times k minus 1, times k minus 2, and so on all the way till 1. And this is precisely k plus 1 factorial. Okay, so then by the principle of mathematical induction, it follows that Sn has n factorial elements for any natural number n. And we are done with the proof. Okay, now we'll prove here that Sn is closed under function composition. Let f and g be two bijections of the set S, which contains n elements. Next, we want to show that f composed with g is injective. So let us assume that f composed with g x1 is equal to f composed with g of x2. In other words, f composed with g of x1 must be equal to f composed with g of x2. And since f is injective, then it must be the case that g of x1 must be equal to g of x2. On the other hand, since g is injective, it follows that x1 must be equal to x2, and consequently f composed with g is injective. Now we'll prove that f composed with g is surjective. So let y be an element of S by the surjectivity of f, we may choose y1 in S such that f of y1 is y, okay, because f is surjective. Now, by the surjectivity of G, we may choose little x in S such that G of x is y1. Okay, now, therefore, thus, f composed with G of x is f of G of x, but G of x is y1, but f of y1 is y. So f composed with G of x is y. So there exists an element in the set x which is being mapped to y under the composition f composed with G. Therefore, f is surjective, and f composed with G is surjective, and we can conclude that the composition f composed with G is a bijection. All right, so here's a challenge from me to you. I would like you at this point to prove the following two claims. The first claim is that composition is an associative operation. In other words, for any three elements in Sn, the following hold true. And then the second claim that I'd like you to show is that Sn has a neutral element or an identity element. So in other words, there exists an identity map, an identity function in Sn such that f composed with this map is the same thing as the map composed with f, and that's equal to f. Now, we claim that every element in Sn has an inverse. So let f be an element in Sn. So by definition, f is a bijection mapping S onto S. And its inverse must also be a bijection, which will denote by f inverse mapping S onto S. So therefore, the inverse of such a function must be in Sn, and then we conclude that Sn is closed under taking inverses. Now, let's have some thought-provoking questions. We've seen that Sn, when endowed with composition, satisfies all properties that the set of the symmetry of the square has. Now, can we study these structures while ignoring the specific elements of these sets? That's a natural question. Can you think of any other sets endowed with a completely different operation which somehow behave just like Sn endowed with function composition? Here's some additional question. Given f and G in Sn, is it true that F composed with G is equal to G composed with F? Is this true? 2. Is it true that if I compose F with G, and let's say F with G, we get F composed with F composed with G composed with G? Can you somehow just move these symbols around as you wish without violating the definitions of these bijections? What are some of the properties that you can think of that Sn has that the set of symmetries of the square do not have? Can you think of any? Can we somehow simplify our quest in understanding the structure of Sn when endowed with function composition by disregarding properties that are specific to the type of element in Sn and the specific operation which is being used in combining elements of Sn? So somehow, can we just focus on the structure inherited by endowing Sn with the group operation without particularly thinking of Sn as being a set containing bijections? These kind of thought, these ways of thinking about mathematics is what we call abstraction. Somehow we gain a lot by proving fact, very general fact, about set of objects which share certain features together, and we gain nothing specific by looking at the individual properties that these elements have, these objects have, which aren't related to the structures that we are interested in. Let us try to go back again and look carefully at S3. So let S be the sets containing element 1, 2, 3. And we consider S3 as the set of all bijections of S. So for instance, the identity send every element to itself. Let's call this map here R. It acting like a rotation. It's essentially just sort of cycling. The element 1 goes to 3, 2 goes to 1, 3 goes to 2. If you compose R with itself, we'll call this here R square. So essentially, if you rotate twice, then 1 goes to 2, 2 goes to 3, and 3 goes to 1. Let's call this here S. 1, 2, 3 goes to 2. Let's call this here U. 1 goes to 2, 2 goes to 3. And V. Okay, so these are all bijections of S. Now let's try to compute R composed with S and see what we get. Well, first we'll start with S. 1 goes to 1, 2 goes to 3, 3 goes to 2, and then we apply R. 3, 2, 1. And notice that R composed with S is in fact U. Right here. You see? Now, what about R squared composed with S? So 1, 2, 3. So if you apply S, we have this. And then we apply R squared, so 2 rotations. Do you see what this is equal to? This is V, right? So R squared composed with S is V. So S3 can be regarded as the set containing the identity map R squared, S, R composed with S, and R squared composed with S. Okay, so I'm going to ask you to keep this example in mind. We'll come back to it. Now, I'm going to present to you another example. And this example will deal with matrices and matrix multiplication. So let's call the first matrix capital R. 1, 1, 0, 0. It's this matrix. And let's call S the matrix 1, 0, 0, 0, 0, 1, 0, 1, 0. And the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. Now let us try to compute R squared, which is R times R. So it will be 0, 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0. And perhaps you remember that to multiply matrices, we'll take this row and this column, and then we essentially take the dot product of these two. So this will be 0 times 0 plus 0 times 1, which is 0, plus 1 times 0, right? So that'll be 0. And then we move to the second column. You'll take this with that. So we'll have 0 times 0 plus 0 times 0 plus 1 times 1. That would be 1. Now we'll have 0. And then for the second column, you consider this with this. Right? So you'll have here 1 times 0 plus 0 times 1 plus 0 times 0. That'll be 0. And you keep going in this fashion. Okay. All right. Now let's compute RS. So for this one, we get 0 here. 1, 0, 1, 0, 0, 0, 0, 1. And what about R squared S? That'll be 0, 0, 1, 1, 0, 0, 0, 1, 0 times S, which is 1, 0, 0, 0, 0, 1, 0, 1, 0. Now, I claim that any arbitrary combination of product of R and S and I will give you one of will give you an element of the set G, where G will consist of the identity, the matrix R, the matrix R square, the matrix S, RS, and then R square S. And you can check that if you take any other combinations of products in any order, you get one of these 6 elements. Now, moving forward, we'll try to see whether this group of matrices endowed with matrix multiplication, which seemingly have nothing to do with the symmetric group S3, whether they behave similarly somehow. We'll try to see whether they have something in common. Is there something about their structure if you just think of them as sets endowed with a particular operation? Can we somehow just disregard the fact that these are matrices in the former bijections functions, and somehow just pay attention to some properties related to the structure that we get if we endow these sets with their respective operation? Okay, so what we'll do here is the following. We'll compute S times R in G, and we'll compute little s composed with R in S3. And we'll try to see whether they have something in common. Well, recall that R is the matrix 0, 1, 0, 0, 0, 1, 1, 0, 0. And S is the matrix 1, 0, 0. Okay, so if we compute SR, we'll have 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0. That'll be 0 here. We get 0 here. We get 1, 0, 1, 0, 1, 0, 0. Again, you can pause and try to verify these calculations for yourself. And if you go back to our previous calculation, you'll see that this is actually precisely R square S. Now, recall that S is the map sending 1 to 1, 2 to 3, and 3 to 2. And R is the map sending 1 to 3, 2 to 1, and 3 to 2. So if we look at S composed with R, then we see that 1 goes to 3, right? And then 3 goes to 2. Now, 2 goes to 3. Oh, no, sorry. 2 goes to 1, and then 1 goes to 1. And then 3 goes to 2, and 2 goes to 3. But recall that R square composed with S was the map. We send 1 to 2, 2 to 1, and 3 to 3. So the map S composed with R is the same thing as the map R square composed with S, just as the matrix multiplication SR is capital R square S. Do you see the similarity between the way when we are pushing symbol, the way we are manipulating how we're combining elements of these sets with respect to the operations that they are endowed with? They act in a very similar way. They act algebraically the same. So is it somehow the case that these structures are essentially, in an algebraic sense, the same? Here is another example that I would like you to think about. You should pause the video here and try to answer this question. If you know, so suppose that somebody told you that the inverse of R, which is R inverse, is R squared in S3. Can you guess what the inverse of R is in the set of matrices G? And can you verify your guess? Computationally, of course. So again, to help you a little bit, your guess should of course be that the inverse of R will be R squared. And to see this, how do you check? You just need to check that if you combine, if you multiply R squared with R, you get the identity. This will be R squared, right? And this here will be R. And you should check that you'll get the identity matrix. Here's another example that I would like you to give you. Try to compute S composed with S composed with R composed with R composed with R squared in S3 and guess what SSR squared is in G, and verify your guess using matrix multiplication. Check that your guess is actually correct. So, in conclusion, what this lesson is attempting to tease out of you, push yourself to find a connection, a meaningful connection in between the two examples. If we are only interested in the structures of S3 endowed with composition and G endowed with multiplication, is it possible to study either one of these structures and automatically gain information about the other? The point here, or maybe the question that one is trying to ask here is it the case that these two structures are essentially, at least in an algebraic sense, very similar? Do we gain anything particular or beneficial by choosing a concrete realization of any one of these objects, or is that not central in understanding the algebraic nature of these concepts? How can we exactly know when two structures, which are seemingly in essence different because they consist of different elements and different operation, but somehow the structure that you get are the same? So they are, in a sense, algebraically identical, or at least similar. How can we do so? Well, These questions are natural questions that we should be asking ourselves as we are embarking in this journey of learning how to get comfortable with abstraction and understanding how important it can actually be to abstract.